Hey class, in this video I'm going to talk about the last three gas laws that we need to know and need to understand, but we do not have to calculate. The first up is Henry's law. Henry's law says that at constant temperature can't change, the amount of a given gas that dissolves in a given type and volume of liquid is directly proportional to the partial pressure of that gas. What does that all mean? It means that whatever the pressure of gases are that surround a liquid, the ones with the highest pressure are going to dissolve faster into that liquid. Now, whether that be a lake, a stream, body of water, an ocean, or as you'll see in next class's module, your body. Say you're scuba diving. When you're under that water, you've got an increased pressure surrounding you and what's inside of you. And something that can happen is you can end up with too much nitrogen in your bloodstream because nitrogen has a higher pressure underneath the water than other random miscellaneous gases. And nitrogen will actually diffuse or effuse into your bloodstream, and it can cause some very serious, nasty stuff. They call that the bends, or sometimes it's known as decompression sickness. I scuba dive, but I've never had that happen and hope to never experience it. But as long as you take the proper precautions and follow the rules correctly, you shouldn't have that problem. So Henry's law comes into play a lot during scuba diving. Second up, Gay-Lussac's law. Gay-Lussac says that pressure and temperature of a gas are directly linked or directly proportional at constant volume. You might recognize this formula from somebody else. P1 over T1 equals P2 over T2. Very similar to, if you guessed Charles' law, you're correct. Except instead of volume, we have pressure. Now, Gay-Lussac's law is pretty common sense. We know that if you increase pressure, you increase temperature, or that if you increase the temperature of something, you're going to increase the pressure because you're going to speed up the molecules by heating it up. And the faster those molecules are going, the more violent those collisions are going to be with whatever container it's in, and it's going to cause an increased amount of pressure as well. Another great example of this is pressure cookers. I don't know if you cook or if your parents cook. Pressure cookers work because they increase the pressure inside that container astronomically, so it makes the temperature increase. And then the higher the temperature that you can get without losing your actual heat, the faster your food's going to cook. That's why you can cook a frozen chicken breast to a cooked chicken breast in about 10 minutes in a pressure cooker, whereas it's going to take you about 45 minutes to an hour to thaw that out and then cook it the old-fashioned way. So pressure cookers completely depend upon Gay-Lussac's law. Another example involving cooking. I like to cook if you haven't figured that out yet. If you and a friend that lives in Denver, Colorado get in a cook-off or a cooking match and you're trying to cook spaghetti, you should always win here in Texas, because water's going to boil at a lower temperature when it comes to the higher pressures. So the higher the pressure, the faster it gets to that boiling point. And here at sea level, or pretty close to sea level, we have higher pressure than do those guys that live up in the Rocky Mountains in Denver. So you're always going to win that competition if if you decide to get in one of those. Not a huge difference. You're not going to finish hours ahead of somebody, but give or take, a few seconds, a few minutes. It is going to be faster to boil with higher pressure. Lastly, Graham's Law. My favorite type of cracker, which I don't know about y'all, but s'mores, that's right up my alley. Particles of low molar mass are going to travel faster than those with larger molar mass. Well, that's obvious. A little tiny particle is going to go faster and be, easier to navigate than a big heavy particle. And a great example of this is, let's take two balloons. You blow one up using your own air. So the one you blew up has CO2, nitrogen, maybe a little bit of oxygen. And then you're going to blow one up using a tank filled with helium. The biggest difference in this is the size of the particles. What happens to that helium balloon when you blow it up? It rises up. Helium's less dense than air, so obviously it's going to float. Your carbon dioxide, nitrogen, and oxygen balloon is going to fall to the ground because it's more dense than air. Now, let's think about the actual atoms inside these balloons. What happens to a helium balloon about 24 to 48 hours after it's initially blown up? And we're talking about rubber balloons. We're not talking about these thin aluminum foil type balloons. Those are different. So about 48 hours, sometimes less, the helium balloon is going to do what? It's going to fall to the floor. The reason is those helium atoms have escaped. They can fuse past that rubber barrier because obviously they have a lower molar mass and they're easier to sneak out. And then what's left is just simply the extra air that was in the tank originally. Usually like nitrogen, carbon dioxide, or oxygen, or a mixture of the three. But you'll notice that helium, once it's out, the balloon does shrivel up a little bit as well too after it sinks. Look at that on a molar mass scale. Let's we'll take carbon dioxide for example, 12.011, and oxygen is 31.998. So that carbon dioxide is 44.009 grams per mole. Whereas our buddy Mr. Helium, he is, let me double check, 4.003. This is CO2, and this is helium. So just looking at that, you would expect helium to be about 11 times faster than carbon dioxide and 11 times more likely to effuse over a barrier, whether that be a rubber balloon, into your skin, etc. So these three laws, pretty self-explanatory. Again, we don't have to do calculations, but you need to understand what each of the three is by definition and how it works or how it comes into play in our everyday lives.